Okay, so then we share screen. Okay, and if you recall last class, no, it's not good here. Put it here. Last class, we discussed neural network, multi-layer, okay, neural network, the artificial neural network. So ANN, you will see that a lot, that or multi-layer perceptron, okay, MLP. Okay, and if you recall that for the input, that we have input then through multi-layer neurons, that to do the training, then we have the output. That so, and over here we have a lot of, we can call it hidden layers. The hidden layers to do the training. So this is X, is it? This is our Y hat is predicted, is it? And so the goal is regarding weight. Okay, so we just need to keep the key concept, is it? So the whole training up goal is to get optimal weights, is it? So that your Y getting close, the Y hat getting close to Y, to the real label. Real labels, is it? And so from input to output through these layers, is we call that feed forward. Feed forward, is it? And but if we use feed forward, and when we try to get the optimize, so optimizing the weights. In neural network, we use gradients. The gradients is, we have the cost function. Or a lot of places also called loss function. Is it? And so the goal is to minimize it, is it? And generally we write as J, is it? And it's regarding weights, is it? So the goal is to do partial derivative with different weights, is it? And in neural network, you have I and J, is it, subscripts. And you try, we try to minimize. So that's the overall goal, minimize the loss function, the loss function. And so we can take a partial derivative, is it? But we said because the weights update, so overall weights update, is it, can be the previous, this is previous epochs, this is weights, is it? And this is, you want to get the current epoch. So epoch is each iteration, is it, for our training from the beginning to the output, is it? And here we have the learning rate, is it? So it's the learning rate times the gradient, is it, times the gradient. So gradient calculation is very important, is it? And the gradient, if you just purely use this, and because this is the weight, you have multi-layers. So here we have multi-layer. So then it's going to involve with some intermediate partial derivative with other parameters. Okay, so, and this is going to involve with heavy, very large matrix multiplication. And in CS, that's always we try to avoid, is it? Because the matrix can be millions, maybe billions, is it? That's not going to work, okay, work well. So we cannot use that way. So basically with neural network, we use the concept to find this gradient, we call it back propagation. Okay, so this is a key concept also, back propagation to update the weights. Okay, not to feed forward to update the weight. We use back propagation to update the weights to find the gradient. So how do we do that? So this diagram shows, so this is the output layer, is it? So output layer. So output layer, we care about the arrow, is it? So this is output layer's arrow is what? Is output layer's activation. So this is activation output, is it? And this is the real label. Real label. As you find the difference between this is the arrow, is it? Because if it is 0, that means you predict correct, is it? So anyway, this is the arrow from the out layer, is it? So the cost function or the loss function take a partial derivative to the corresponding weights. So here is the weights, ij out layers weights, is it? It's going to be equal to what? So we don't need to use the mass, the big matrix multiplication to find the derivative. So from mass, the mathematician already find the relationship between the derivative and the arrow from the out layer. Okay, out layers are not output layer. The arrow at the output layer. So it's going to be equals to what? So this is a vector. This is a vector, is it? And what is it? This is the hidden layers activation. Hidden layer, the activation output. Output basically is from this layer. This layer. So the gradient will be equal to this two value multiplication. Okay, so the multiplication between these two, then it's much smaller compared with the other. You take the multiple chain derivative. Okay, so we can find the derivative, the gradient, is it? Gradient for the output layer. And then you can then correspondingly update the weights, is it? Leading toward the output layer. So then the same idea, that's why we call it a back propagation. That's why we call it back propagation. Is it? So you from the output layer, is it? You find all of the weights, is it? And then let's see. So now we come to the hidden layer. For the hidden layer, the arrow at a hidden layer, so yesterday we also discussed, it's the relationship with, so the arrow at output layer is delta out, is it? And from the previous, we also find out the weights for the output layer. That's the weights. So W out, is it? And we also find delta out. So the arrow, is it? So you times that, and then what? And then you take, this is hidden layers, net input. Net input. The net input, so it's what? It's the weight times the corresponding previous layers. So this is input layers activation output, is it? and you take derivative to this. And this is also easy to find, is it? And if we take a look the previous yesterday's discussion, what that is, if you recall, the derivative of the activation function, is it, regarding the net input, then it's going to be just the activation output times, so this is element-wise multiplication, the times 1 minus that hidden layer's activation output, is it? So this we also know. Is it? Then from this, you can find the hidden layer arrow. Is it? So that's why we say it's back propagate. Back propagation. So you push arrow from output layer then to hidden layer. Is it? And then once you have this hidden layers arrow, then the corresponding layers derivative, the gradient, we can also find the same thing. It's the input layers activation output times the corresponding arrow. Is it? And once you find this, then you can update the corresponding weight. Is it? Because it equals the previous epoch's weights times the learning rate and the derivative, the gradient descent. Is this? So then we can get the current epoch's weight. Is it? So we can find this. Okay, so that's the general idea about back propagation. Okay, back propagation. So it make use of the arrow at each layer, but the arrow at hidden layer depends on the arrow from output layer. And each previous layer's arrow depends on the next layer's arrow, is it? And also the weight of next layer, is it? And the current layer's derivative of its activation function regarding its net input, is it? Okay, so that's how we the basic concept about back propagation. Okay, so we kind of understand the general idea about the back propagation. So next, let's see the example. Okay, about neural network. Okay, training. So here we use the wine data set, and this wine data set, you can also get it from the classic machine learning data repository. Okay, so here we will show how to use MLP. Previously, we also discussed, it's basically just that ANN, is that it's multi-layer perceptron. Previous at the beginning of machine learning, we learned a single perceptron. Is that now we discuss multi-layer. Okay, it's also called artificial neural network. Is it? So it's the foundation of deep learning, So we use that wine data. Okay, the wine data, it's basic data frame looks like this. Is it? And the total you have 178 samples. Okay, so and we have a certain number of features. Is it? Each feature to also give us. So here, so we have 14 total. We have 14 columns. Is it? So we are going to use 13 features. Is it? We are going to have this column as our y value. Okay, so let's see. And if you see the coding part is not that comprehensive or compare with neural network itself, the concept. The concept itself, because it heavily involves all sorts of math. Okay, so that's why it's complicated. But like I just explained, we just kind of need to understand how feed forward work, how back propagation works. Okay. So the first steps saying we do train, test, split, etc. And always remember, okay, for neural network, you need to do data pre-processing, bring all the data to the same scale, okay? So here we do standard scalar, okay, standard scalar. And then we feed, we transform both training and testing data, okay? So nothing new here. And then in order to do the neural network, is it in sklearn, you can use sklearn's neural network. And it has the multi-layer perceptron, the artificial neural network's module. Okay, so here we can use the MLP classify. Okay, and here we use it to classify, etc. And with this model, etc. And here we specify the hidden layer size. And be careful. Okay, here we have 3 hidden layers. 3 hidden layers, and each layer has 13 neurons. Okay, each layer has 13 neurons. So you have 3 hidden layers. Is it? Oh, 3 hidden layers. Is it? So just remember, okay, each neuron, is it? So here you have input, the X, is it? So each neuron, it contributed to the next layers, each neuron. So here you have the weights. Okay, you have the weights. And each neurons, it gets a contribution from the previous layers, all of the neurons, is it? And the net input, so this is net input, is what? Is the sigma, Wij, is from all of the previous layers. Okay, from all of the previous layers, times what? Times A, is it? A, so A is what? A is from the previous layer, apply certain activation function. Okay, activation function, previously we learned linear activation function. Linear activation function, then we have the add line, is it, for the single neuron, is it? And what else we have learned? Who remembers activation function? Any other activation function we learned? Who remembers that? We learned sigmoid. Is it? You remember sigmoid? And there are some other like tangent, is it? But we didn't see any of the examples. Okay. And later on, we will also see ReLU used a lot, okay, in deep learning, okay. Okay, so anyway, so here we have 3 hidden layers, and you also specify neurons, okay. And this is the maximum number of iterations, okay, iterations. Okay, and then let's see, then you feed the model, is it, with the training data. And here, let's take a look, the classifier, some default settings, is it, parameter, like activation function, we didn't specify. So by default, it uses that ReLU. Is it, it's rectify a linear unit. Linear unit, okay. Generally speaking, in deep learning, we don't recommend to use sigmoid or tangent. We don't recommend, okay. because there are some issues regarding gradient, the gradient kind of leading toward disappearing. Okay, so there are some issues. So that's why we use rectify linear unit. And rectify linear unit, basically it's just some max function between 0 and the x. Okay, so it always take, positive part of the value x. Otherwise, if it's negative, it will take 0. Okay, that's what, so it's quite simple, is it here? Okay, and this also support batch size. So you can also specify batch size. Okay. And what else? Okay, here for the solver, so here it's basically for the gradient. And here to use adder. Is it adder? And who still remember yesterday we discussed the solver? Is that there are 3 kinds of solver? Is there 3 kinds? So atom is one, and the other one is what? Stochastic gradient descent. Is it? And both of this, and we said they support stochastic processing. Who remembers? Who still remembers the key concept about stochastic?
Online.
Yeah, it's online. And what does online mean? What does online versus offline? Offline, we also see another word.
Batch.
So generally, yeah, batch. Very good. Is it batch? So stochastic, it's online. So it's not to do the weight calculation with regarding the whole sample space. Okay, it's use a single sample to do the updates. So that's the concept. Okay, and generally speaking, we do online or mini batch. So mini batch means you don't use the whole sample space. Is it? You can divide it into some small batch and then start processing. Is it? So regarding space efficiency, is it? So this is regarding space efficiency. Okay, anyway, so here just keep that in mind, the solver. Okay, solver here means gradient. Gradient, okay. So gradient is the gradient calculation, is it? So it's also related with optimization, okay. So that's the key concept here, okay? Because we do need to know at least this basic stuff. Is it? Otherwise, it's kind of fancy, oh, deep learning, deep everything. But what is that? Is it a lot of parameter we need to know? Oh yeah, I just mentioned that ReLU, is it? It's called rectified linear unit, is it? What is rectified? So it's a rectified, it's an activation function. Is it activation function? And the activation function, you remember the very first one we learned, the activation function is what? We can call it unit function. Oh no, I'm sorry, that's a wrong concept. Unit step is regarding the output. We learned the linear, is it? Linear, basically it's just the function itself, is it? So we have that phi z, basically it's z, is it? So that's linear, is it? And then we learned sigmoid, is it? And sigmoid is the 1/1 plus EZ, is it? Something like that. So that it can smooth out, is it? And now we have the concept, it's called rectify. Okay, rectify is what? Basically, it's just this function. and it says X is the input to the neuron. Be careful, it's input to the neuron doesn't mean it's the input sample, okay? So this can be X, as it can also be A. As it A is activation output. As it this output is like the hidden layer. Is that with all of the hidden layers, you don't have X, is that you can only have A, okay, so be careful. So anyway, so that's rectify linear unit, ReLU, okay. So you see this a lot in deep learning, so what that means, we know that. And then we can just do prediction, as it a prediction, and you can also classify, you can also collect what? Collect the performance, is it using matrix, confusion matrix, and accuracy, is it? Here we can see the result is pretty good, it's a 98. Okay, so that is this one, pretty simple. And then next, let's take a look at the next one. The next one, yeah. Okay, so this time, if you recall the MNIST, who still remember what is the MNIST?
It's for digit recognition.
Yeah, it's for the digit, single digit number. Is it for 0 to 9? Is it handwritten single digit recognition? Is it? So MNIST, that is very classical one, okay. So previously, I remember we learned using some other machine learning approaches, is it? This time we are going to see how do we use neural network to train the classification, is it? And total it has 7,000 samples, is it? And the dimension is 784, is it? And who remembers what is this 784, the dimensionality? Who remembers? Because for each image, you have width, is it? And you have height, is it? And you have all sorts of pixels, is it? So what is 784? That means the number of pixels, the width, and the number of pixels of height, is it? And the pixel value is between 0 to 255, is it? So each pixel, that's compose your image, is it? Okay, so anyway, so here we kind of turn 2D, is it, to 1D, 785. And I remember it's 28 by 28 something, is it? Okay, so let's see. So anyway, so from sklearn, you can also get the MNIST data, download the MNIST data, okay. And if you recall, is it, and we can also see the image, is it, if you recall, from the data set, is it, you can also plot the corresponding image, is it? So here it shows, is it? So your purpose is after you train with neural network, you have the model, is it? And next time when you have a handwritten, is it a handwritten image, it's 28 by 28, then your algorithm can correctly predict, is it, what the number is. Is it, this is kind of like face recognition, is it image recognition? So the simplest case of image recognition. And it's used a lot right now, okay? It's also similar like voice recognition, is it? So all sorts of this. similar concept, is it? So anyway, so here it shows the original data, is it? So it's some number between 0 and 255. And the same thing, we need to do data pre-processing. Okay, data pre-processing. Okay, let's repeat this question again. So the standard scalar, what is its purpose? What is the purpose? Who remembers that? So this is regarding data pre-processing. Is it? Data pre-processing, there are a number of ways we can do, is it? There are a number of things we need to take care. Yeah, okay. Any other one has the answer about standard scalar? Who remembers? Resizing, yeah, okay, it's yeah, it's very close, but generally we don't say resize, we scale data. Okay, so what we mean is we bring data to the same scale. To the same scale, generally, we consider like -1 to 1. So you bring all of your data to kind of this data range. Okay, so that when we use gradient to do the training, we won't have some skewed data be generated. Okay, so that's the purpose. This is one of the most important part, okay, in machine learning. You need to bring data to the same scale, okay? And there are generally two ways. One is called standard scalar. The other is normalization, okay? And then you fit and you transform the data, etc. So nothing new here, okay? Some review. And then next, let's see. Over here, then same thing, we import the machine learning MLP, is it a neural network model, is a multi-layer. And we also going to use accuracy score, is it? And for this neural network, we just have a single hidden layer. And the number of neurons is 50. Is it 50? And the maximum number of iteration is 10. Okay, is 10. And this is for convergency. See, some tolerance. Okay, you won't let it go forever because the goal is to approach to 0. Is it the arrow? The arrow approaches to 0. Is it? And here the solver we specify, we use what? So what SGD means? Who remembers? SGD is what? What is S? Pardon me?
Stochastic gradient descent.
Yeah, very good. Yeah, you can send your answer to the chat. So it's stochastic gradient descent. Okay, so that's what SGD. So it's one of the solver. Is it one of the solver? And here it also has a verbose. Okay, so in neural network, we use this a lot. So because it takes time to training, okay, to training later, especially for deep one, you will say it's very slow, is it? And the verbose, you can have 0, have 1, have 2, and here it has 10. Okay, what it means is, if you recall in computer, a lot of time when you do uploading, is it, or some conversion, it says the progress bar progress bar, is it? So if you set it as 0, it won't, so it do off the processing silently, and you will just get the final result. So until it finish, it let you know. Then in the middle, you have no idea. So generally, I don't like that, is it? Because you have no clue, is it? And if it has 1, then it give you process bar with each iteration, each epoch, is it? And it also shows you for the first iteration how far it goes, is it? So you have the clear clue where the processing right now is it? With 2, it tells you it won't have progress bar, but it will tell, okay, iteration 1 and the result, iteration 2, the result, something like that. Okay, so that's the verbals. And here it also specifies the learning rate. Okay, learning rate. So those are all of the common parameters you need to be careful. And then you can fit the model, you can predict the model, you can also get accuracy score. The accuracy is pretty good. Here you see, even though you said the maximum iteration is 10, that means if it goes if it completes 10th iteration, and if you still didn't get the desired result, it won't continue, it will just stop there. Okay, but here if you take a closer look, it didn't complete all 10 iterations. Why? Because the tolerance, is it? This value already reached this, the specified, is it? So it's already converged. So that I said, because this is a threshold, so convergence is threshold. You define, you said, okay, here this kind of level of error, I'm going to stop, is it? So it's convergence threshold already reached, so that's why I'm going to stop, okay. Okay, so that's this concept, that's this example. And so basically we are done with multi-layer neural network example, okay. What next we are going to start with is the TensorFlow, okay. So today probably we can just get some basic idea, and tomorrow we can. It's regarding deep learning, okay. So TensorFlow, okay, like over here says. And on my slides, I also have some link how to install TensorFlow on your local machine, okay. Otherwise, you can use the Colab, Google Colab, then you don't need to worry about the installation of TensorFlow, okay. Anyway, so we can also, because once you train some example, because with that the data is not that large. So if you have larger data set, the neural network training with our MLP, it's very slow, it's quite slow. And because in that case, we didn't do parallel processing, okay. Here it says training neural network parallel with TensorFlow. Okay, so that's one of the benefit part. And also, we also know TensorFlow is one of the most popular deep learning, okay, libraries available right now, is it? Okay, and the Python language itself, be careful, okay, it's limited to execution only on one core. Okay, so the language itself is not multi-threading. Okay, not like Java, you can do multi-threading, as it is as due to this global interpret locker, as it interpret locker. But if you recall, when we do sklearn, is it we can also take advantage of multiple core. Is it you remember specify with that jobs parameter? Is it the jobs? It will also allow you to do multiple core. Is it multiple core? But even with that, with deep learning, large data is still not efficient, is it? And right now we want to use more and more about GPU, graphic, is it? Graphic unit, is it? Processing unit. Okay, the graphic card basically says can be viewed as a small cluster, computer cluster. So it's like some multiple computers, is it? When you learn cloud computing, you learn cluster concept, is it? So you can view a GPU kind of within the machines, the cluster, is it? And because it's GPU, it's a graphic processing unit, is it? And with graphic, just think about it, it's all pixels. Is it all pixels? And generally speaking, like this patch, you see, these two patch won't impact, not rely on each other a lot. Is it? So you can completely isolate them, put them into a different processing unit. Is it? You can parallel processing them, is it? And then finally aggregate them, is it? So that's why we have, so GPU support that, is it? So that's why we say it's like a small computer cluster, okay? So that's the concept, okay? And it says the challenge, right, to target GPU, there are a lot of challenges, is it? In the past, it said also some special package like CUDA, is it? OpenCL, is it? But it's for machine learning, it's take a lot of time. Is it not a very good platform? Is it? So TensorFlow, when TensorFlow comes out, this is a very good platform, okay, for parallel processing for machine learning. And the TensorFlow is that it's scalable and also multi-platform programming interface, okay? It supports machine learning, is it? And especially for deep learning, we use a lot, is it? And the TensorFlow, the key point, it rely on what? A directed graph to represent data flow. Okay, that's the key point. So TensorFlow, it has some directed graph, okay, graph. And even though it says building graph will be very complicated, later on we will see, okay. But TensorFlow now also has a high level, like Keras, is it? It's high. So TensorFlow, it has a low level API, and it also has a high level API. Okay, with the low level, we will see it's very complicated. Okay, good thing is with the high level, well, it's quite straightforward. Okay. Okay, so here it shows the high level and the low level as an API. And TensorFlow, the concept is built upon graph, directed graph, okay? So be careful. And because it's graph, of course, it has nodes, is it? And it has edges, is it? And in TensorFlow, each node represents what? Represents some operation. Okay, so are you going to do add or multiplication, those kind of operation, is it? So that's regarding a node. And because it's a graph composed with, is it? Node and edge, is it? So what is edge? The edge is whatever the value flows through the edge, is it? So that's what our A value and our X value, those can flow into the nodes. Okay, and TensorFlow, then you have the concept of tensor, is it? So tensor is a math concept, is it? It said it's generalization of scalars, vectors, and matrices. Okay, so it's all from math, is it? And scalar generally it's rank 0 tensor. Okay, vector is a rank 1 tensor, and the matrix is a rank 2 tensor. Okay, rank 2. And you can stack matrix in third dimension, rank 3 tensor. Okay, so all of those are math background, and we don't need to worry too much. And so we run out of time. Okay, so tomorrow I think we should be able to finish TensorFlow and its examples. Any other question before we